Hi students, so today we start lecture 38 and now we are going to discuss about the range and endurance of an airplane. So these are two very important concepts and they happen to be different when you apply them to propeller aircraft and jet aircraft. I'm Dr. Ranjan Ganguly. So the endurance of the airplane, we can define this as the total time that an airplane flies in the air on a tank of fuel. So that's the definition. So from this definition, we clearly see that this involves time and therefore endurance can be measured in seconds or minutes or any such temporal unit. The symbol we used for endurance is E and therefore we are going to derive equations today for this particular value of E. Now, where is endurance useful? You will see that there are many aircraft which need to perform reconnaissance or surveillance missions in the sense that they need to take off from an airport, they need to hang around in the air for a long time, they need to survey large amounts of territory. For example, they may be in the Coast Guard or the Navy and they may look around the sea or the ocean for different boats, for any survivors of any wreckage and so on. So in all these situations, you essentially have an aircraft which has been designed for endurance to be maximized. Now, there is a different metric which is often used for performance, and that is range. And range is the total distance measured with respect to the ground traveled by an airplane on the tank of fuel. So again, range is something which we are more familiar with. For example, when we are going from airport A to airport B, we travel a lot of miles or kilometers, and this is essentially the range. But do keep that this range is measured with respect to the ground. Now, the unit of range is meters or kilometers, and typically we use the symbol capital R to define range. Now, if you ever encounter some things in miles, you can remember that 1 mile equals 1.60934 kilometers. So again, that will help you convert your problem from the mile system to the SI system. Now range becomes useful in any commercial aircraft, like I told you, any aircraft flying from point A to point B, but also in cargo, and there are certain military missions also where you may design an aircraft for range, for example in bombers and so on. So there is a very important concept known as specific fuel consumption, which is going to help us to get an expression for endurance. So specific fuel consumption, also known as SFC, this is a property of the reciprocating engine propeller. We are going to later look at this concept for a jet engine, but today we are going to look at the propeller concept. So here we say C is Newton of fuel divided by joule per second into second, and this value for the specific fuel consumption is specific to a given aircraft which has a reciprocating engine propeller combined, such as the one I have shown here. Now, from this definition, we can extract certain facts about time. For example, if we look at the dimensions of C here, we see that joule per second is basically power, and of course, second is time. So if I take these two values to the left hand side, I can say that Newton of fuel is same as C into P into dt, where C is the specific fuel consumption, P is the power, and dt is of course a very small amount of time which has elapsed during this period. Now this equation is going to help us to get the equation for dt, which is time or related to time. Now before we do that, let us look at various weights which are there with respect to an aircraft. So when the aircraft takes off, it essentially has a weight of W subscript 0. So this is the gross weight of the airplane. Now you can sometimes remember gross with this 0 or O here, and gross weight is the full fuel and payload weight. So it's the completely full aircraft with passengers, with fuel and so on. This typically happens when the aircraft takes off from an airport to fly for a mission. Now WF is the weight of the fuel load, W1 is the weight of the airplane without fuel. So that is W0 minus WF. So that's an important equation to remember, that W1 is W0 minus WF. Now, W is actually the total weight of the airplane at a given time. So, those weights we looked at, W0 and W1 and so on, they are the weights at the beginning and the end of the mission. But during the mission, the weight of the aircraft is constantly changing because the fuel weight keeps changing. So, W is the fixed structural weight plus the payload weight minus the fuel weight. So, remember that you are starting off the journey with the full tank, but at the end of the journey you have an empty tank. So essentially W keeps changing, and therefore if we were to take the derivative of W, we will see that dWf is dW is minus Cp dt. So essentially this is the equation we are dealing with here, because of course fuel is being expended and hopefully none of your structural weight has gone or none of your payload has been jettisoned. So in that case this equation will hold. Now from this equation we again get back to our equation for time, which is dt is minus tw by cp. Of course now we have to integrate this equation to get the time from dt. So here we start with this equation for dt and we integrate it to get endurance. So essentially at start t is 0, w is w0, your fuel tanks are completely full, and at the end of the mission t equals e, w is w1, so your fuel tanks are totally empty. Now you can integrate this particular dt value, and if you integrate it you get this value here. Now of course you know from integration that I can absorb the negative sign inside the integral provided I flip these bounds on the definite integral. So that's what's done here. The w0 goes up, the w1 goes down, and then the minus sign gets absorbed here. So we get this value as E equals integral w1 to w0 dw by Cp. So this is the value, and this value is going to give us endurance, but we are also interested in range. And for range what we do is that we multiply this dt by v infinity, and so we get ds is v infinity dt is minus v infinity dw by cp. So like I mentioned before, range of the aircraft if you are flying from point A to B is essentially the distance which is traveled during this period, and of course if you are talking of the time, that is endurance. So dt is a small amount of time between this journey and ds is a small amount of distance in this journey, and we are going to have to integrate it to get the actual range and endurance. So let's look at range. So this is the equation for ds, and so ds was like this. Again at the start of the journey s is 0, w is w0, that is full tank of fuel. At the end of the journey s is r, w is w1, that is the empty fuel tank, and therefore I can integrate ds from 0 to r, and that's going to give me this integral here. So at 0 w0, at r w1. Now what we can again do is we can flip these bounds of the definite integral, and if we do that the negative sign will disappear. So this is something coming out of the theories of calculus. So in the yellow here we have the expression for range. Now we can look at all these integrals in a way which we do in classical calculus. So again what we do in the endurance integral is that if we had 1 by Cp and we had variation of this with respect to W, then I basically need to find the area under this red curve that is going to give me the endurance, and each of these dWs are essentially small changes in W which are happening during this process when you are going from the beginning to the end of the journey. So this is the integral you need to find for endurance. If we consider range now, remember the integral for range, we had V infinity by Cp. So if we plotted V infinity by Cp with respect to W, we would get something like this. W is going from W1 to W0. And so this is going to give me the integral here. So now we can see that both these integrals can be found, but these integrals are generally valid. We have made no approximation. So we can clearly see that equations are valid for the entire flight. So takeoff, climb, cruise, and landing. So what we need are instantaneous values of W, V infinity, C and P. If we have these values, we can calculate these integrals, and you can take recourse to numerical integration to do this calculation. So if you do that, you can get numerically accurate solutions for the endurance and range. Now, in many cases, we want closed form or simple solutions, so we can do that in some cases by making approximations. So just to recapitulate, this is the general formula for range and endurance, and we were looking today at the propeller cases. So we actually will show in the next two lectures that we can get closed form solutions like this for range and endurance. So these are values which are coming out of these integrals in nice closed form solutions, and these are going to reveal certain things about the physics of the problem to us also. Finally, to summarize this very important concept, we see that endurance is the total time that an airplane flies in air on a tank of fuel, and range is the total distance measured with respect to the ground traveled by the airplane on a tank of fuel. So essentially, the assumption here is of course that you start with a full tank and you end up with an empty tank, and with that we get these particular integrals, and if we have these variations with respect to W, we can find these integrals from numerical integration. Remember, there are techniques such as trapezoidal rule, such as Simpson's rule, which easily let you calculate these integrals. So if you have taken any kind of class on numerical analysis, then you know how to calculate these integrals. If not, we can of course find closed form solutions, but they are going to be approximate. They are only going to look at certain cases. They are not going to look at the landing, takeoff and all. They are going to look at only the steady level flight. So those are the equations we are going to derive over the next four lectures, and next two lectures I'm going to concentrate on the propeller, and following that on two lectures I'm going to concentrate on the jet engine. So I'll end my video now, and I will see you in a video sometime soon. See you then.